first part, so we just managed to do the derivation of the natural growth, the law of natural growth, which is a formula that you are familiar with since, high school, intermediate algebra, or pre-calculus, But again, back then they just told you, oh, this is the model that we use, where P initial equals KT. If K is positive, well, this model represents growth. If K is negative, this represents decay. You can use this to solve problems about population growth or radioactive decay, or the cooling of an object using the Newton's law of cooling, And but now that we know some differential equations, we can now tell where this equation, where this function is coming from, which is by solving this differential equation. But that's not the only model that you've seen before, so you might remember this one. The compound interest, when the interest is compound continuously, right? It looks exactly the same. In a similar way that the population grows, gets bigger. Well, so this accumulated represents the total money that you invest in a bank account or in a business. Well, depending on the context about this, whether it's a business or just a bank account, right? So let's solve a very brief problem on using this law of natural growth. So, what do we have? A community has an initial population of 20,000 and continuously grows at a rate of 5%. So we can start label our pieces of information. This is our P initial. That's an initial population, and the rate, which is 5%, that's actually K, but we don't write these numbers as percent. We actually change them to their corresponding decimal versions, which in this case is 0.05. Alright, so let's write down a formula and plug in these values. Well, so P of t at any time is P initial e to the kt. And well, plugging in the numbers that were given in the problem, P of t equals P initial, which is 20,000, e to the 0.05 t. Well, so we have a model that can determine the population size after any time t, in this case years. So in this case they're asking us to estimate the value of the population after 10 years. All we have to do is substitute t equals to 10, and well, this should be approximately 32,974 people. Alright, and this makes sense because, well, it's population growth. Initially we start with 20,000, so we would expect to get a larger number, right? So that should make sense. But the thing here is, well, that model is a very fictional model because, well, if you think about, consider the size of this room here. So, and suppose, well, not the room. Maybe consider the entire city, San Diego, right? So if we use this population model, for example, that we can plug in a value for t equals to 10, t equals to 40, t equals to 100, the population after 100 years, well, we would be getting a larger number every time. But if you think about it, is San Diego big enough to carry millions of people, 20 million people maybe? I don't think it's big enough, right? So that's a situation with the entire planet, right? It's not big enough to handle so many people. So that's what we call the carrying capacity, which is the maximum size a place can carry a certain number of people. And in this case, we're going to adjust to a new model, which is the logistic model. Well, so the logistic model is very similar to the law of natural growth. In this case, we still have this KP, We still have this kp, but we also have this other factor right here, and that factor is a factor that depends on population size and carrying capacity of the city, the country, or an entire planet, right? So, and well, the initial condition in order to solve this differential equation is again the fact that P of 0, I didn't type it, but I'm going to write it, is the initial population. All right. Let's solve this equation to find a mathematical model adjusted to the logistic model. Well, so this one is not going to be as easy as the one that we did last time with the law of natural growth. This one is going to take actually a good minute to go. So, in fact, we're going to go back to partial fraction decomposition in order to get this one, right? So, okay. So let's try and separate the variables as usual. In other words, well, if we had an equation that depends on x and y, get the x's on the right hand side and the y's on the left hand side. In this case, our dependent variable is p and independent variable is t, so we need to have all the t's on the right and all the p's to the left. So let's multiply both sides by dt to get dp equals kp. 1 minus p initial, no, it's not initial, just p over m dt. And notice these two factors, p times 1 minus p over m, those two factors depend on the variable p. So what I'm going to do is divide those two on both sides to get dp divided by 1 minus p over m. And that equals to k dt. We're essentially ready to integrate the right-hand side because what's the integral of k dt? That's just going to be kt plus c. Yes?
What happened to the p?
It's supposed to be here. Thank you. Thank you.
Is the p minus p squared over here?
Do you mean by distributing? I'm not going to distribute because if I distribute, then I would need to factor it back to get the partial fraction decomposition. So we're going to leave it like this for now. However, what we have to do in this case is simplify the left-hand side a little bit, because in this case, we have this complex fraction, this ugly-looking fraction. I mean, it's a big fraction with a smaller fraction inside. So that's going to be horrendous when it comes to finding the constants a and b that split this into a sum or difference of partial fractions. So what I'm going to do is multiply both numerator and denominator by m. So multiply across and multiply m times 1 and multiply m with p over m. What's going to happen in this case? Well, so that's going to be m dp over p times 1 times m, which is m. And notice how when we distribute the m over the quotient p over m, the m's get canceled. That's just p. And see how friendly this looks like? It looks a lot better than its predecessor in this case. So, well, so I think we're ready to integrate. Okay, the integral of k dt is simply k times the integral of dt. But we need to work on this one, and I'm going to take a side strip here. I'm going to do that on this side. So let's see, the integral of m dp over p times m minus p equals, well, in this case, notice the dummy variable is p. It's not x like we did before, or even y, the different letters. So in this case, it's p. That means we are going to have 1 and 2 different factors to split. In particular, these two factors are linear and distinct because p is to the first power here and also p is to the first power as well. So we're going to split this integral as a over p plus b over m minus p. That with respect to p. All right? Recall that in order to find these constants a and b that split the fractions together, all we do is set these two equal to each other as an equation. Let me use a different color for that. So that's going to be m m dp, well actually just m over p, m minus p over a, equals a over p plus b over m minus p. Alright, well, let's simplify this equation by multiplying both sides by the least common denominator. And well, that will be the product p m minus p, p m minus p. And well, what's going to happen here? Number one, when we distribute over the left hand side, these two factors are going to get canceled, and that's going to leave us with m equals to, so when we distribute this, m times p times n minus p. Nope. So the p's cancel, and over here when we distribute with the second factor, the n minus p's get canceled. That's going to leave us with the following: a times m minus p plus b times p. And remember how we call this? Isn't that our basic equation? That's the equation that we use to find the unknown constants a and b. And if we recall from the method, well, I think it's good review for the upcoming exam in which you will be tested on partial fraction decomposition. So we need to find clever values of p in this case, not x. In this case, we're not integrating with respect to x. So we need clever values of p that can zero one of the terms, so we can find the other, one of the letters, one of the values, and then figure out another clever value that cancels the other term, so we can find that coefficient, well, depending on the order a or b. Can we think of a clever value for p? M. All right. M sounds good because, so p equals m. Well, use, so for p equals to m, because if we plug in m here, that first term is going to get zeroed out, and we will be able to find that value of b. So let's see. So m equals to a times m minus p, which will be m, I'm going to do that in a second, plus b times p, which is also m. Let me write it with the corresponding color so you can see why are we plugging in and where. Alright, so this term to begin with is going to get zeroed out. Oh, that's fine. And we're going to be left with m equals to bm. Dividing both sides by m, that b becomes 1. So b equals 1 for now. Alright. Now, can we think of a different value, another clever value? Well, now we need a value to zero the second term so we can find the value of a.
0.
0, right? Because, well, if p equals to 0, yes, of course. So for p equals to 0, m equals to a times m minus 0 plus b times 0. And I'm going to write that 0 with red just so you can see why and where are we plugging it in. So that's going to leave us with m equals a times m, which is am, and this is going to get zeroed out. And again, dividing both sides by m, that's going to give us a also equal to 1. Alright, so let me go back to the integral right here and write down a equals to 1. Well, that's only the side work. So we need to get back to the original problem, the original integral, the one that we were initially solving in blue right here. Alright, so this integral right here, which we broke down over here, will become the integral of 1 over m, or rather 1 over p plus 1 over m minus p with respect p equals k times the integral of dt. So we may go about the integration of these two terms on the left hand side. Alright, yes.
After you complete this, do you mind us showing us how to do the fraction decomposition with the system of equations as well?
You can do it with the system of equations as well. So you can use the clever values idea, which usually is shorter, but if you do it the system of equations way, that might be a little bit more time consuming. So in some cases there's no way around to the system of equations way, because in some settings these clever values doesn't work, like the example we did in class. That last example that took almost a whole lecture, we had to go the system of equations way. So in this case you have the two options. You can do it either way. So integrating this, so what's the integral of 1 over p? Isn't it ln of absolute value of p plus ln of m minus p? However, this plus becomes a minus because of the correction factor when we integrate that. When we set up that du, that du becomes a negative du. And well, what's the integral of k dt? That's simply kt plus c. Again, recall that we only add a constant of integration on the right hand side of the equation. It's an accumulated or an already absorbed constant of integration. Okay, let's do some algebra here. Let's go back to pre-calculus and look at a bunch of properties of logarithms. Remember the quotient rule or the difference rule? Whenever we have the difference of logarithms, that's the quotient rule, right? A over b. So I'm going to write this as a quotient. Ln of absolute value of p over m minus p equals kt plus c. Well, over here, I think we're ready to exponentiate both sides. So we can keep trying to get a function of p, to solve for p by, to let p by itself, right? However, when I first did this problem, go exponentiating at this point, I got into a big madness, into a big hell, and I struggled a lot to get the final solution, or the solution that I desired. So I'm going to use another property here. So there is, you can switch, so ln of a over b. You can always reverse the order of the quotient to b minus a, provided you have a negative outside of the logarithm. Alright, so that's another property. Well, it may not be a property that they told you to memorize back in pre-calculus, but it's actually a result of manipulating these, these logarithmic expressions. And well, I'm going to write a negative ln of m minus p over p equals kt plus c. Alright, so now trust me, this one is going to be a lot more friendly to go about if we treat it this way. So let's multiply or divide by -1 so we can keep solving for p. So that's ln of absolute value of m minus p over p equals, well, -1 multiplied by kt, that's negative kt. But what happens when we multiply a constant of integration times -1? That remains a c. It's still a c, right? By absorption. Alright, so at this point we may go about the exponentiation on both sides. And well, number one, on the left hand side we're good to go by canceling this ln with the e. However, be careful on the right hand side, because for a sum or difference of terms, when you exponentiate that all those number of terms, this exponentiation will affect all of the terms right here. Alright, and well, we have done this a few times. Let me continue here. Well, this is absolute value of m minus p over p, that equals to e to the negative kt. But again, what's e to the c? Isn't that just a c? Right? Now, what about the absolute value bar? So I mean, At this point, we may go about getting rid of those absolute value bars, because again, what if I do this m minus p over p? Oh yes, I mean, we would have to do this plus or minus c because of the definition of solving an absolute value equation. Remember that equation, x minus 3, absolute value of that equals to 2. That's technically x minus 3 equals plus or minus 2. All right, we solved two equations. One set it equal to the negative value, one set it up to the positive value. But in this case, it's safe to just get rid of the absolute value bars without having that plus or minus, because plus or minus c, what's that going to be? Just c, all right? Okay. Let's keep solving for p. So number one, how about we split this fraction right here, m over p equals negative p over p, minus 1. So the reason why I use this weird property of logarithms to flip the order of the quotient is because if we left it in this order, we wouldn't have been able to distribute the fraction the way we are able here. Alright? And that's going to simplify our lives a lot. So number one, let's keep solving for p. So add 1 to both sides of the equation. That's m over p equals c e to the negative kt plus 1. And well, so we may go about multiplying both sides by p. Multiply by p, cancel, m equals to, okay, I know this is going to tempt you to distribute the p, but don't distribute the p, because if we distribute the p, that p is going to get absorbed with the c, and we don't want that. In fact, we're just going to leave it like that for now. So this will become m equals to p times c e to the negative kt plus 1. And well, we are only one step away to get the p by itself, which is by dividing both sides by this madness here. So p equals m c e to the negative kt plus 1. So yes.
Is there a reason you can't distribute it, subtract it, and then move n to the other side?
It would give us a different result because of the absorption with the c. It would that p would disappear by the absorption with the c.
Even when you distribute it to the plus 1?
To the plus 1, yes. I've done it before, and when I compare my result, it gave me something different. So this is our general solution. Finally. General solution. Now we need to find the particular solution. So with p of 0, that's the initial population. Alright, this means again that when t equals to 0, p equals to p initial. In fact, what we're going to do is plug in t equals to 0 over here and replace p with p initial and find an expression for c. Don't worry about m. That m again is that factor of carrying capacity, which will be given in the problem that we're going to do shortly. All right. So okay, p, which is p initial. Yes. That's p initial equals m divided by c e to the negative k times 0 plus 1. Alright, let's simplify this. Okay, so for the exponential factor, so we have a negative k times 0, that's 0, and then that's the same as saying e to the 0, which is 1. But what's 1 times c? Isn't that just c? C plus 1 in the denominator, and p initial. So we need to solve this rational equation for for C, because notice how C in this case it's in the denominator, so you might want to think of this P initial as P initial over 1 and try to solve this for C by cross multiplication. Alright, so that's going to be P initial times C plus 1 equals to M. And dividing both sides by P initial, that's C plus 1 equals M over P initial, and just subtract 1 from both sides. So that's going to be C equals to M over P initial minus 1. Yes?
Why isn't C plus 1 just C?
Yeah.
Because that's because this is not just a constant, another constant. It's actually a value of 1. It's not another constant of integration. So for example, that's a good question. So we can do this absorption when we have C1 plus C2, which is simply C, or C1 minus C2, which is also C. And we can do this absorption thing when we have, I don't know, maybe C1 times 2, for example, or any number, that's just C. Or C1 times C2, that's simply C. Or the different operations that we have, like exponentiating, or C, which becomes another C, e to the C equals to C. Even ln of C, it's also just another C, but when we have a known number, that doesn't get absorbed. Alright? So let me erase all this. So, well, we need to simplify this quantity right here. Think of this as over 1, and multiply numerator by P initial and denominator by P initial to combine them together into a single fraction. So that's M minus P initial over P initial. And this is our constant of integration, which, check this out. This constant of integration right here should be replaced with C here in our general solution. However, if you think about it, we would be plugging in or substituting a fraction inside of another fraction, which will create a lot of trouble with complex fractions, right? So you don't want to do that. In fact, instead, how about just give it a different name? For now, call it A for now. And that A will get calculated separately when we look at these applications. So in this case, our general solution here will become particular solution P equals, or rather P of T equals to M divided by A e to the negative kt plus 1, with A equals to M minus P initial over P initial. So that's our particular solution finally. Alright? Okay. So let's go about one example. And well, so let's see. Alright, so write the solution to the initial value problem dp dt equals 0.08 p times 1 minus p over 1,000 with an initial condition of p of 0 equals to 100. Well, if we did what we just did of solving this differential equation symbolically, well, we would have done the same process but with numbers. But lucky for us, we already have a mathematical model just ready to plug in values depending on what we have from the equation. However, I'm going to relate this equation with some values with the generic version of it. That is, in this case, the dp dt equals k p 1 minus p over m. And the reason for this is that we're going to use this to relate. This 1,000 represents our m, which is the carrying capacity factor, and this 0.08, which multiplies the p. That's our rate, well, in this case the constant rate. And I think that's about it. Oh, one more piece of information. This is going to give us our initial population. P sub 0 equals 100. All right. Okay, so let's go about the solution. Let's write down the solution to the equation from the previous page. Let me write it again. P of t equals to m over 1, or a rather, e to the negative kt plus 1, where, well, in this case we need to find that value of a. Remember, we gave it a separate name, so that's a equals to m minus p initial over p initial. And, well, so m, which is the carrying capacity, so that is the maximum amount of people in the community that can be carried, so that's 1,000 minus the initial population of 100 divided by the initial population of 100. So let's simplify that. 1,000 minus 100, that's 900. Divide that by 100, that's 9. So we can go about P of t equals, well, I'm going to take care of the m here. Well, m is 1,000, a, which is 9, e to the negative k, which is 0.08, t, and then plus 1. All right. So we have a mathematical model only between p and t that we can use to get what they're asking us for. That is the population after 40. Well, let's assume it's years, because usually we measure population sizes per year. So it doesn't say anything, but let's assume it's years after 40 years and after 80 years. That is, essentially, all we have to do is evaluate P of 40 and P of 80. So that's 1,000 divided by 9 e to the negative 0.08 times 40 plus 1, and 1,000, 9 e to the negative 0.08 times 80 plus 1. This should be approximately 731.6 and 985.3 approximately. And, well, in this case, well, we would be expecting some population growth. However, this model is not going to give us a population growth that steep in the growth as opposed to the law of natural growth, because in this case this model is considering the carrying capacity of the system as opposed to the previous model. All right. So this is it for the chapter, actually, and today we're going to start a new. Yes, I'm going to skip that part. So, okay, infinite sequences and series. So, yes, we're going to go from chapter 9 to chapter 11. It doesn't mean that we're not going to cover chapter 10. So, chapter 10, we're going to cover at the end of the semester during the last couple of weeks or so. So, we're going to spend a good minute looking at chapter 11. It's one of the longest chapters ever. We're going to deal with infinite sequences. Then we're going to look at infinite series. And well, so essentially we're going to look at different techniques to determine whether a series converges or diverges, in the same way that in a few chapters ago we look at different techniques to evaluate integrals, right? So it's something similar. It's about techniques, different techniques. And, well, so before looking at the infinite series, let's define what a sequence is. So number one, a sequence is a special function denoted curly braces a sub n, sometimes without the curly braces, sometimes just a sub n. And, well, but the thing here is that the domain of these special functions It's only the set of natural numbers or all positive integers. Well, that's because we would be looking for the first term of the sequence, the second term of the sequence, the third term of the sequence, etc., the nth term of the sequence. And well, think of you guys participating in a competition to win the first, the second, and the third prize, right? In this case, we're talking about natural numbers. You either win first or second or third. But can you win the 2.5th place in the competition? That's something weird, right? Or the 1.9. No, that's kind of weird, right? So same for the sequences. So we're not going to look at the 3.5th term of the sequence, the 1.9. No, it's the first, second, third, fourth, etc. All those terms. All right. So another way to denote these infinite sequences is by having these limits in a similar fashion as the sequences as the limits of integration. Yes.
If it's a sequence, can we just also, if we're adding infinite numbers, can we just also write this in sigma notation?
That's going to be the series, because that's a good question, because for a sequence all we're going to do is list the terms of the sequence. However, for the sigma notation, that sigma means to add, and that's the infinite series, to add those terms in the list. Good question though. All right, so we need, sometimes we use this limit, this lower limit, upper limit, to denote where we are starting our sequence. Or like whether we're starting at the first term, the second term, third term, etc. But in some cases, we may start. The most common starting index is n equals 1, because that's the first positive integer, n equals to 1. But in some cases, we may have the need to start at n equals some k, another number, starting at n equals 2, n equals 5, n equals 4. Well, that's going to depend on the nature of the function that we are relating the sequence in particular, depends on its domain. You will see an example in which the sequence will start at n equals to 1, and one in which start at some other value. Okay, so let's get some practice on this. So let's write or list a couple of the terms here, a few terms. Well, of course, this is an infinite sequence. We're not going to write infinitely many terms. We're just going to write a few. So all we have to do is plug in n equals to 1, comma, n equals to 2, comma, n equals to 3, etc. Depending on the question, you might be asked to write the first 5 terms, the first 4 terms. I'm going to do the first 3 terms here. And we're going to start with n equals to 1. So that's the square root of 1 over 2 to the 1 minus 1, comma, the square root of 2 divided by 2 to the 2 minus 1. That will correspond for n equals to 2. And the square root of 3 over 2 to the 3 minus 1. Now, again, because this is actually an infinite sequence, I'm not going to write infinitely many terms. I'm not going to do infinitely many calculations. We don't have time for that. We still have to make sure that even though we are only expanding the first 3 terms of the sequence, we still need to give a sense of infinite, and that's like comma, dot, dot, dot. And with this, we denote that this sequence goes on forever, infinitely many terms. Okay, let's simplify this. The square root of 1, which is 1, over 2 to the 1 minus 1. But 2 to the 1 minus 1 is the same as saying 2 to the 0, which is 1. Comma, square root of 2. And that's 2 to the 2 minus 1, which is 1, or 2 to the 1, which is 2. And square root of 3, which is the square root of 3. And that's 2 to the 4, 2 to the 2, which is 4. Comma, infinitely many terms. And you might want to simplify this 1 over 1 as a 1. Alright? And well, of course, if we continue this pattern, that has to be, well, without doing the calculation, the square root of 4 over 2 to the 3rd, which is 8. The square root of 5, which is 2 to the 4, which is 16. And square root of 6 over 32, comma, and this simply goes on forever. Okay?
So empirical way?
Yes, that can be reduced. That can be reduced for sure, because this would involve powers of 2 that can be reduced further. But it's easier to leave it like this so we can see the pattern if the question is backwards. So given the sequence, find a general term, which is we're gonna do in the next page, but maybe next time. All right, let's have a look at letter B. So for letter B, what do we have? -1 to the n times the square root of n minus 2 from, notice the starting index is not anymore n equals to 1, it's actually n equals to 2. Well, let's talk about the different elements of this series in particular. Number 1, I would like to talk about this -1 to the n power. That -1 to the n power, well, depending on the parity of the value of n that we plug in, 1, 2, 3, 4, 5, well, depending on whether it's even or odd. So recall that in this case, if we raise a negative number, in particular -1, to an even power, that remains +1. But if this -1 is raised to an odd power, that becomes a negative. Well, so this will cause the sequence to alternate between positive and negative, positive and negative, positive and negative. For this reason, this particular factor, it has a special name. It's called an alternating. It's an alternating factor. And well, later when we get more in depth into infinite series, we're going to dedicate a special section to study this alternating series. This series that will contain these alternating factors. Now, what's the reason why we cannot start the sequences just our favorite value? Well, we need to be very, very careful, because if we look at the function related to this sequence, that's f of x equals the square root of x minus 2. So in this case, we need to take the domain of the given function into consideration. And to find the domain of the radical function, set the radicand greater than or equal to 0, solve for x. So in this case, this last statement is telling us that the domain of the function is only the set of values that are greater than or equal to 2. That means we cannot start the sequence at n equals to 1, because it's not part of the domain. In fact, if you plug in 1 minus 2, you're going to get the square root of -1, which is the imaginary number I. And well, this is calculus of real functions, not calculus of complex functions. There's a special class for that in this here at SDSU, Math 532, functions of complex variables. You will get to look at those series, at those functions that are complex valued functions, but that's going to be later. Actually, a lot of you that are engineering majors, electrical engineers, civil, any engineering, eventually you will get into this calculus and algebra more in depth for complex valued functions. Well, in the meantime, let's talk about real numbers for now. So let's start writing down some elements of the sequence. So that's -1 to the second, that's the first index, square root of 2 minus 2, comma, -1 to the third power, 3 minus 2, comma, -1 to the fourth power, square root of 4 minus 2, comma, dot, 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 that goes on forever. All right? Let's simplify this. Well, the square root of 2 minus 2, well, that's the square root of 0. No matter what is this is just 0 for the first term, all right? And, well, -1 to the third power, that's going to cause the next term to be a negative number. And then 3 minus 2, which is 1, square root of 1 is 1. And then what do we have? 4 minus 2, that's just 2. The square root of 2 is simply square root of 2. But that -1 to the fourth power, it's an even power, that will remain positive. And of course, if the pattern continues, that'll be the square root of 3, the square root of 4, the square root of 5, the square root of 6, the square root of 7. And well, in the alternating pattern also continues. So that's positive, negative, positive, negative, positive, negative, positive, negative, comma, dot, 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 infinitely many terms in this sequence.